Todas as substâncias são feitas de moléculas. Cada molécula é feita de átomos. Os átomos, por sua vez, são feitos de elétrons e um núcleo. O núcleo atrai os elétrons com força elétrica e magnética. Isso era o que se sabia até o início do século XX. De lá para cá, descobriu-se que o núcleo também tem partes internas. Ele é feito de prótons e nêutrons, que ficam presos um ao outro pela força nuclear. Na década de 60, os instrumentos da física ficaram mais potentes e mostraram que prótons e nêutrons são feitos de partículas ainda menores, os quarks. Eles também se ligam por força nuclear. No universo atual, só os quarks para cima e para baixo são usados para construir substâncias. No início do universo, havia outros tipos de quarks. Eles hoje estão extintos, mas podem ser recriados a partir de energia pura nos laboratórios. Os dados coletados dessa maneira revelam que só existiram em todos os tempos 6 quarks: para cima, para baixo, estranho, charme, em cima e embaixo. Bastam esses 6 ingredientes, mais os elétrons, para se montar tudo o que existe.
O físico britânico nascido na Nova Zelândia, Ernest Rutherford, contribuiu para a fundação e o desenvolvimento da física nuclear e da moderna teoria quântica. Ele estudou a radioatividade e a natureza das partículas alfa, carregadas positivamente. Sua descoberta mais importante foi a natureza da estrutura do átomo. Ele percebeu que a carga positiva de um átomo está concentrada no centro, num minúsculo e denso núcleo. A liderança e o trabalho de Rutherford inspiraram 2 gerações de cientistas. Em 1908, recebeu o Prêmio Nobel de Química e, em 1925, foi escolhido presidente da Real Sociedade de Londres.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked 2 of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounce right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounce off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away. After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing them at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
In 1803, the brilliant scientist John Dalton was able to prove in the lab what the ancient Greeks thousands of years earlier thought might be true, that matter was made of incredibly tiny building blocks called atoms. Dalton thought that atoms were solid spheres like billiard balls, and that they were the smallest particles in the universe. But about 100 years later, scientists discovered that atoms were made of even smaller particles. This video shows how they were able to do that. In 1897, a clever Englishman called J. Thomson designed a glass tube filled with low-pressure gas and containing two metal plates inside. When he put a big electric charge on the plates, he found that the positively charged plate, called the anode, was able to pull a beam of tiny particles out of the negatively charged plate, called the cathode. Because the beam came from the cathode, he called them cathode rays, and he called the apparatus a cathode ray tube. You can see the beam as a blue line in the diagram. Where the cathode rays arrived at the anode, there was a little hole that allowed them to travel through and continue and pass between a pair of parallel plates that he could put varying charges on. Sometimes the top one was positive with the bottom one negative, and sometimes the other way round. The beam always bent away from whichever plate was negative and towards whichever plate was positive. This meant that the particles must have carried a negative charge, because we know that like charges repel and unlike charges attract. But here's the thing. Because the beams bent so easily, more than other particles going through the plates, he could work out that they must have been very light, thousands of times lighter than a hydrogen atom. Thomson realized that atoms had even smaller particles inside them, and that they carried a negative charge. He had discovered the electron. He won a Nobel Prize for this. J. Thomson was not only a brilliant scientist, he was a really good bloke as well, and he helped many of his students become famous scientists too. 7 of them went on to win the Nobel Prize, including his own son. One of his students was Ernest Rutherford, an extroverted New Zealander with a booming voice and a big laugh. Rutherford was playing around with beams of positively charged particles, which he called alpha particles, that were emitted from uranium atoms. He knew they were positively charged because they bent in the opposite direction to the electrons of a cathode ray when passed through charged parallel plates. They bent more slowly than electrons, so he knew they were heavier than electrons too. Rutherford used these alpha particles as atomic bullets and fired them at a very thin sheet of gold that was only about 1,000 atoms thick. On the opposite side to the uranium source, he placed a scintillation screen that lit up when particles hit it, so he could then measure where the alpha particles landed. If the gold atoms were like billiard balls, then the alpha particles would be blocked and none would arrive at the screen. Instead, almost all the alpha particles passed straight through the gold foil, as though it wasn't there. Rutherford realized that the gold atoms were mostly empty space. J. Thomson thought that the mass of atoms was pretty evenly smeared out within the substance, and he also thought that most of the alpha particles would pass through. But something very surprising happened. Some of the particles were bent a few degrees off course, and about 1 alpha particle in 20,000 bounced right back in the direction from where it came. Rutherford said at the time that it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. What this meant was that the mass of the gold was not evenly spread out at all, but concentrated in very small lumps that were positively charged. He had discovered the atom's nucleus. Because the nucleus was so small, most alpha particles didn't even come close and completely missed them. They went straight through. If some went close to the nucleus, its positive charge would cause repulsion and bend them off course. If an alpha particle made an occasional direct hit, it would bounce right back from where it came, because the nucleus was much, much heavier than the alpha particle itself. The nucleus is incredibly heavy. Over 99% of the atom's weight is concentrated there, and incredibly small. If we magnified an atom to be the size of a football stadium, the nucleus would be the size of a pea. Rutherford later discovered a particle inside the nucleus that was responsible for its positive charge, and he called it the proton. An atom's overall nuclear charge was equal to the number of protons it had in its nucleus. And this also turned out to be the same as the atom's atomic number. Each element had its own number of protons in its nucleus. How's that for a coincidence? But there was puzzling evidence that the nucleus was heavier than could be accounted for by protons alone. Scientists could measure the weight of protons, and they knew how many protons were in the nucleus of each kind of atom. But when they measured the overall mass of these nuclei, they were usually about double the mass of all the protons put together. Was there another particle in the nucleus? In 1932, James Chadwick, a student of Rutherford's, discovered a beam of new particles with about the same mass as protons. He did this by shooting alpha particles into beryllium atoms and knocking these particles out of the beryllium nuclei. The beryllium target was much thicker than Rutherford's gold foil, so there were many more nuclei for the alpha particles to make direct hits with. Beryllium's nuclei has an atomic number of 4, so he knew that they had 4 protons each, but he was experimenting to find a new particle in the nucleus. When these particles were struck by the alpha particle bullets, they were knocked out of the nucleus and then continued in a beam that Chadwick could study. This beam did not bend when passed through charge parallel plates, like the electrons of Thomson's experiment did. Remember, it was the electron's negative charge that made them bend when going through the plates. This meant that the newly discovered particles had no charge. Because these particles were electrically neutral, he named them neutrons. Chadwick had an eventful life. During World War I, he was a prisoner of war in Europe, and he even did a lot of his experiments while he was a prisoner. Then during World War II, he helped invent the atomic bomb in America. By now, scientists had a fuller picture of how atoms were made. They had a nucleus consisting of positively charged protons and neutral neutrons at their centre, and this was responsible for most of their mass. Light, negatively charged electrons whizzed around the outside of the nuclei, in fact at about 3/4 of the speed of light, and gave atoms most of their size. The question of how atoms could stick together was also answered. Having an opposite charge to the nucleus, electrons are attracted to it, so the electric forces can hold electrons travelling at near the speed of light and bend them into an orbit around the nucleus. Electric forces act as a kind of atomic glue holding atoms together. They are quadrillions of times stronger than gravity. For those of you who have learnt about the powers of 10 way of writing numbers, electric forces are 10 to the power of 33 times more powerful than gravity. That's 1 with 33 zeros. In the next video, called Atomic Structure, we will look at how electrons are wrapped around the nucleus in shells, and how this dictates the properties of atoms. For example, whether they will be a gas, liquid or solid, or their colour or brittleness, or whether they will be a metal or a non-metal. Pretty much everything.